Welcome everyone to today's webinar, E3 certification for VTOL aircraft. I'm Nicole Van Dusen of EMA. I do have a few housekeeping items before we get started with the presentation. I did send out a reminder yesterday, and in that email, there was a notification that the Teams platform does show that your profile is visible upon logging in. If you'd like to participate anonymously, I just want to remind you that you can click the three dots under your profile and select Hide Me from the menu. Our speakers today are Cody Weber, co-owner of EMA and principal scientist, and also Matt Miller, co-owner of EMA and principal RF engineer. We've allotted 30 to 45 minutes for this presentation. That includes time for questions at the end. Feel free to enter any questions that you have throughout the presentation into the chat box, and then we'll address those. And we had a few questions that came in via email that we can address at the end as well. This session will be recorded and sent to you after the presentation, and we will follow up with you directly. So if you're interested in scheduling a time for a discussion afterwards, either myself or Matt Bradley will be following up with you directly, and we can coordinate that for you. We can go ahead and get started. I'm going to go ahead and turn it over to Cody.
Thank you very much for the introduction, Nicole. Thank you everyone for joining. Before we get into the topic of the day, I just will introduce our company briefly. EMA stands for Electromagnetic Applications. We specialize in E3 RFI expertise with aerospace companies around the world. We've been doing consultation, simulation, and testing for over 45 years now. And the different areas that we consult in are lightning, HIRF. Those are the primary topics of the E3 webinar today. RFI, which Matt will talk about. We do a lot of EMI, EMC work, talking about bonding, crosstalk, the different radiated and conducted emission susceptibility kind of environments. We do work in P-static and then some non-standard EM environments as well. This concerns spacecraft charging, surface and internal, and then also EMP environments. So one of the things that set our company apart is the ability to do the three areas, being able to consult, being able to simulate, and be able to support testing. And so we can tie those three together and we can use them to support your company in ways that perhaps other companies cannot. So again, thank you all for joining today. For the webinar, we're going to start with the E3 environment. I'm going to talk mostly about HIRF and lightning. We're going to review some of the regulations and standards associated with them. We're going to discuss a little bit about the specific complexities of eVTOL aircraft. Then I'm going to dive a little bit more into the HIRF topic and lightning topic and some consideration points that you may find useful. And then I'll touch a little bit on simulations and how we use them to support those activities. Matt, for the RFI topic, we'll talk about installed antenna performance, RF interference, and then also arms measurement capability that we have. So quick background about eVTOL and certification. I'm sure many of you know, you're on the call today, you're interested in eVTOL. It's a new aircraft type with no certification heritage. And so there's no alignment within the authorities across the world in what is the exact process to achieve certification. Now you can go forward and treat them like a Part 23. If you're in Europe, it's EASA. They have the SC VTOL category, and you can utilize the guidance documents and certification approach that exists for regular aircraft. Well, there are some unique aspects of these designs for these aircraft, considering that they're battery powered. They're all electric, some of them. There's lots of CFRP materials and other lightweight materials, and they're rather small. And so if you're considering what makes a good protection for E3 traditionally, and say, well, I need metals and I need plenty of protection, good amount of size to help conduct currents, good bonding platforms, and those really aren't inherently part of the VTOL. There's ways to add them back in, but it takes some careful consideration, which make the certification and design aspects of VTOL quite unique compared to other aircraft. This is just a snapshot I pulled. If you do a Google search of eVTOL, a lot of different images pop up. There's some very unique designs. Some of them look like some traditional aircraft, some look nothing like it. So it's quite a wide range of aircraft types within this segment. I just listed here the regulations that would exist if you were certifying under a Part 23 aircraft with the FAA. We'll talk through a few of these more in depth today, but you have to know what the regulations are and how they apply to your aircraft. You're obviously certifying your airplane. There's regulations for lightning protection. One, direct effects. It must be able to withstand all lightning events. You need one for electronics and electrical systems. This is your indirect effects. There's the HIRF regulation, your airplane level EMI, EMC, and then there's some hybrid aircraft as well. And if you are a hybrid, electric and traditional fuels, you must be aware of the fuel system protection. And there's a lot of work that goes into that for traditional aircraft. I'm not going to focus on that today. I'm going to focus on the fully electric version. So if you're looking at the SC VTOL regulations, it's the same numbering system as the Part 23, but it just has the SC VTOL designation in front rather than the CS23. And when you're preparing to certify your aircraft, it's very important to make a certification plan. This is where for each of those regulations, you identify how you're going to achieve certification, how you're going to verify a safe aircraft design for all the different E3 environments. I have them listed here. I'm not going to go through all of them, but for HIRF and Lightning, primarily it's AC, which are advisory circular documents put out by the FAA and the authorities. There's the policy statement documents. One of them in particular we're going to talk through today is also put out by the FAA. Then there's largely ARP documents put out by SAE committees, which have an industry agreed upon approach or process to certify your aircraft in those different environments. And they're very important to consider when going about this process. Another aspect that's critical is not only the certification plan, but your E3 control plan. This is how you will identify for each of these different environments the design that will take place for your particular aircraft, how you will achieve the protection, and any important aspects of the design that you need to consider for that. So one of the points that gets brought up quite frequently is what kind of tests do I need to perform on my aircraft? And if you're doing traditional aircraft certification, some of the full vehicle E3 tests include an EMC test. This is where you verify functionality of your equipment, that it all plays nicely, operates as you intended to. Then there's the HIRF full vehicle test. There's a couple different ways to approach this. You can do high-level testing, but more commonly, I believe it's the low-level testing that people do. This is where you illuminate your aircraft, measure attenuation in certain areas or bays, and then also record the currents that are conducted on your cables. Additionally, you'll have to do a full vehicle lightning test. And so this is an LTA test, lightning transient analysis test. And this is something that is, all of these tests require an entire aircraft or a representative aircraft to do. It takes a lot of time to plan to do these tests, and it takes a lot of effort, both labor, technician-wise, testing-wise, in order to complete these efforts. So it's a big commitment, both schedule-wise, vehicle downtime-wise, and labor-wise, to complete these. And once you've done vehicle tests, there's an aspect of verification that has to be done with your system or unit level. And this is where you set up your systems, identify critical functions, and then perform your HIRF and Lightning testing on your individual systems to verify safe operation. One of the interesting parts of Part 23 regulation concerning HIRF and Lightning is that there was a white paper put out by the SAE AE2 committee a few years back. The FAA recognized the value in that document and turned it into a policy statement. That's the PSACE 2310 document. And what this document said is that for small aircraft of a certain class, I had the class listed on the bottom of the screen here. It's dependent on size and operation and number of people that the aircraft can hold. You can use lookup tables to specify your indirect effects lightning environments and your HIRF test environments for the system level. What that means is you get to bypass doing the full vehicle test for HIRF and lightning, which is, it drives a lot of cost and there's a lot of complexity associated with that. There's some arguments that are made in these, the policy statement document and also the ASTM F3367 document, talking about how Part 23 aircraft can utilize these set levels and still achieve an adequate level of safety. And so we'll go through that a little bit more. What I have listed on the right is the flow chart talking about how you go about utilizing these. Pretty much any certification effort starts with identify the functionality of your equipment. So you do an airplane assessment and a safety analysis associated with your equipment so that you understand what groups you have to make with your systems and what levels you have to apply. One thing that I want to point out with this table is that as the aircraft gets smaller, so Class 1 being the smallest aircraft, Class 2 being slightly larger, 3 bigger than that, Class 4 being up to 19 people that they can hold on the airplane. As you get to Class 4, it identifies you have to do the traditional Part 25 method for certification, where you have to do that full vehicle testing and the whole route that way. But as you get down in level from 3 to 1, Class 1 has the lowest level, so it's the smallest airplane. And if it gets struck by lightning of the same amplitude as one of the others, you wouldn't expect the amplitude to go down, you'd expect the amplitude to go up. So there's something involved with that assumption in the policy statement document about lower lightning amplitudes being applied for the smaller airplanes. And that's an important point I'm going to touch on here in a minute. I'm not going to read through this, but basically in order to utilize those lookup tables for HIRF and lightning on Part 23 airplanes, you must meet a minimum design requirement list. And it basically says if you're using metallics, you're bonding them together, you have good current paths, you're doing some shielding based on the structures of the airplane. If you have composites, you're adding in protection on the skin with metal mesh or metal foils. You're carefully considering how you will bond the different components together to conduct current safely and to provide shielding on the inside. And so you don't just get to use those lookup tables because you have that size of airplane. You want to make sure that you're doing some level of E3 protection in order to do that. Okay, so I said that's for Part 23. Well, are eVTOL Part 23 aircrafts? As of now, within the FAA, yes. But there's no guarantee that you can use the same certification approach for eVTOL that has been done for Part 23. And I don't think it's likely in Europe. That if you read through the SC VTOL specification for aircraft, there's really not an allowance to use those lookup tables. And basically every category of eVTOL is sort of in the enhanced category, which says you have to go the full route that includes the full vehicle testing for HIRF and lightning. And so it's important at the beginning of your program or whatever stage you're at to consider, is that a right approach for me? If I have a Part 23 airplane, can I use those lookup tables for my HIRF and lightning system level specification? It's a very important consideration. I'm going to go a little bit farther onto the HIRF side. So I think there's some differences between HIRF and lightning and the way that industry is talking about doing the full vehicle test for the two. From AC 20-158, it's about the HIRF compliance approach. There's a process that you follow. There's steps that you need to undertake sort of one by one. Sometimes you mix between the levels as well in order to certify your airplane. And I'm not going to go through these in detail, but whenever you're doing the process, it's important to understand what are the steps that need to be followed for certification. This is a flow chart that breaks it out, and it's obviously very simple that you just start at the beginning and work your way through. One of the ones that I jest, but it's if you know what you're doing, it can be done in a straightforward way. Those with aircraft certification experience sort of understand the nuances that belong within each one of the individual sections. And if you've not done it before, it can be kind of tricky. So it's useful to have people to reference or to talk to this about in order to establish your path. The one that I have highlighted is the aircraft low-level coupling test. And that's the one that I think is most common for the full aircraft HIRF testing. And the image on the right-hand side is the subset of low-level coupling tests, being the low-level current and low-level swept field. There's also the aspect of the low-level direct drive. I'm not going to get into that for now. So what we have seen in discussions with authorities and in discussions with industry is that most likely the eVTOL will have to do full vehicle HIRF testing. There's an aspect of operation where they will be in urban environments more frequently than other Part 23 aircraft. They will be performing their functions in areas that perhaps has not been understood as well for what the RF environment will be. And so it seems at this point that it's unlikely that the Part 23 eVTOL will get out of doing full vehicle HIRF tests. So I think it's something that should be accounted for. Once you have that planned in your certification route, you also must decide what is the right HIRF environment. Is it the normal environment? Is it severe rotorcraft? That's another discussion point that needs to be had with the authorities, that once you're doing this establishment of HIRF environment and how it couples to your aircraft, what is the right level to apply? So I think as of now, within discussions of the community, you should plan for doing HIRF full vehicle tests. Once you have done your testing and you have your attenuation levels and your coupling to your cables, you follow the Level A systems compliance steps. I'm not going to go through this in detail. I put it on here that if you need to review it and you want to learn more about it, please look through it and you can ask questions later. I'm going to move on to Lightning now. So we talked about HIRF and the expectation that most likely there will be full vehicle testing. That may not be the case for Lightning. For Lightning, there's two different types of effects that most commonly are considered. One is direct effects, one is indirect effects. Some people don't like that split in term, but I think we can all understand the difference in effect by labeling it that way. Direct effects has to do with puncture, destruction of components, ignition of fuel, which may not apply for eVTOL, but some physical destruction of a vehicle according to the lightning strike. Indirect effects is the coupling of lightning currents to electronics cables and a transient that develops that could upset or cause a failure to your electronics equipment. And so the way that you approach the certification for both of these depends on your lightning environment, your zoning, and some other effects. So I'm going to jump to the lightning environment now, because this is an important consideration point for these small aircraft type. I'm going to go back to the policy statement ACE 23-10. There's an argument made in there. Before I mentioned the smaller the airplane, the lower the environment, and that may not be intuitive. What that comes from is this data that exists for lightning strike occurrence to small airplanes. And what has been found is that the smaller the airplane in terms of dimension, and here they classify in terms of length times wingspan, smaller the airplane, the less likely it is to be struck by lightning. And so they have strike rates per flight cycle that are dependent, and there's a clear correlation between the size of the airplane and the strike occurrence. And the eVTOL and smaller airplanes are down in this lower left-hand corner here, and that they've broken this out in the document to show that these strike occurrences are really small for these very small airplanes. And they use that argument to say the smaller the airplane, the lower the environment they get to use for it, because it's less likely to get struck. I'm going to read the quote here that they state within that document. It says, the smaller the airplane, the lower the likelihood of a lightning strike occurring. This correlation provides a means to adjust and standardize lightning test levels to account for exposure risks and the airplane size. So they're saying that it's less risk of exposure for the lightning, and it's a smaller and smaller airplane, therefore it gets to use smaller levels because it's going to be struck less frequently. It may not be intuitive for everybody, but now there's a precedence within this document for that consideration. If you've gone that route and you're using those lookup tables, you don't have to do full vehicle testing. And so that may be an option for these eVTOL aircraft in the Part 23. And so keep that in mind, that if you're certifying your airplane to lightning, you get to utilize these tables. You have classified your airplane 1, 2, or 3, whatever it is, and you meet those minimum design requirements, you may be able to utilize these lookup tables. One thing that, in my mind, is a disconnect is that if you're allowed to use a smaller indirect effects lightning environment, why can't you also utilize a smaller direct effects and lightning environment? So that if you're acknowledging that it's a smaller airplane, it's less likely to get struck, I can consider a smaller airplane environment for indirect effects. Why cannot this also occur for the direct effects side? And so there's discussions going on in industry right now about what is that appropriate environment. The traditional lightning environment is 200 Ka. If you go out, you protect your airplane to 200 Ka with all your tests that you have to do for direct effects, you're going to be fine. But there could be some difficulty associated with that with the small airplanes, the lightweight materials, and everything associated with that. So one of the things that's being discussed right now is, can this small likelihood of being struck for small airplanes also adjust the external environment? So that if you have a small airplane, you have operational conditions that maybe limit the amount of exposure time you have to lightning environment, that there's different lightning distributions based on amplitude, there's different peak current distributions and the probabilities associated with them. Is it possible to combine these different inputs based on industry data to reduce that overall level for direct effects purposes? There's nothing that prohibits you going this route and pursuing this evaluation for your particular aircraft. And I think that it is an interesting point that hopefully we'll get there eventually. What is the right direction for these aircraft? But there's no consensus on it right now. But it does not prevent you from pursuing this route for your airplane. So how that impacts some of your design and certification testing, that if you have to do a full 200 kiloamp protection for your composite skins, probably there's a way you can get there to do that for ECF that you've coated on top, other protections of that kind. Is it still going to work for all of your motors, for your windshield, which required special consideration for all your control surfaces and joints? It's something that if you had that reduced environment, it could make a big difference in the way that you protect your airplane and the weight that's associated with those protections. Lastly, I just list here the indirect effects certification process, that if you're going the full airplane route of doing the LTA testing, establishing your transients, you go through this process here in order to do that verification. So I talked about HIRF, I talked about lightning, the full vehicle testing associated with it. We also specialize in doing simulations, that if you're going to be doing designs, it's very beneficial to do a numerical model to help tell you whether or not your designs will provide the protections you need. And so that if you have your simulation model put together, you can do sensitivity analyses, that if I use this type of protection, what does that afford me? If I switch to this protection, how much higher do the levels go up? And so that early problem identification can translate to a large cost savings within your program. The sooner you build the model, the sooner you can use it to drive and guide design decisions. And then also there's a growing awareness within the community about using certification for simulation. Right now within the AE2 Lightning Committee, we're putting together a document called Sim for Cert, Simulation for Certification, where we are making an ARP document that says this is how simulation can be used to support certification for lightning environments. It can be used to reduce program testing and then help to do evaluations of your design post-certification. Both of these methods, the design and certification side, are greatly beneficial for aircraft programs. Here's a snapshot of the tool that we use. It's called EMC Plus. It's made here at EMA. We develop it, we take care of it, but ANSYS is the distributor of the product. What you get with EMC Plus is 3 solvers in one. We have our full wave finite difference solver we call EMA 3D. There's the M-harness multi-conductor transmission line solver and a circuit solver. And what we can do is a full model of the airplane down to the pin level and circuit level in a single simulation, which is very powerful for E3 evaluations. We have done a lot of validations with this approach. The techniques that are utilized, the way that you build these models can be compared to testing to show that these numerical techniques are valid for E3 programs. Here's a snapshot of different types of environments we can analyze. You can do lightning for direct and indirect effects evaluations. You can apply a HIRF environment to look at attenuations and coupling to cable. If you have a vehicle mock-up and you have your cables in there, you can drive signals on your cables to look at the emissions or coupling to nearby cables. And then also we can do a lot of system level evaluations. According to DO 160, all the RS, RE, CS, CE environments. An interesting aspect of numerical analysis that would be beneficial for eVTOL especially is being able to look at field enhancement, so that if you have to zone your aircraft for lightning, you can apply an external field in terms of a step leader source or a plane wave, and then look at how the field enhances around the vehicle. It's called electric field modeling, and what that does is allows you to establish where the maximum enhancement occurs and what are the most likely places on the aircraft to be struck by lightning. This is one of the environments that is being included with the Sim4Cert document to say this is a great benefit of using simulation for your programs. I think this is my last one, but what I meant before by using simulation to establish E3 environments is that if you have your design and say you have your cables routed to your extremities from your cockpit to your rotors in the rear or your propulsion motors in the front, and I have a certain type of cable shield on it, I have a certain weight of ECF on my aircraft. Well, what does that mean for my protection and my levels? What you can do with the simulations is you can vary that in a sensitivity analysis and show that as I increase the protection on the outside, here's what it does to my transients in terms of bundle currents and in terms of pin protection for pin voltages. And that you can use that to help guide decisions about what is the appropriate amount of protection I need for indirect effects protection. So it's one of the things that can be done with the numerical model. I'm sorry, I did have one more. Of course I did. The HIRF coupling simulations, that if you're doing the lightning evaluations, you can also use the same model that you've developed for HIRF evaluations. And you can apply that external field and you can envelope results for LLSC. And you can also look at attenuations that occur in the different bays. So there's a lot of benefit to be able to do that analysis and guide your decisions for E3 compliance. That was the last one. Now I'll pass it over to my colleague, Matt Miller. Matt, please go ahead.
Okay, thanks, Cody. Yeah, so while Cody talked about HIRF and lightning and survivability related to those two topics, I want to switch gears and talk about antenna performance and radio frequency interference. Sometimes this is called co-site interference. It's really the same thing, just two different terms. And I want to spend a few minutes and talk about a measurement capability that we have here at EMA called ARMS, which is the Automated Radio Measurement System. Next slide. So there are two primary problems that we tend to think about when we consider RF systems on eVTOL platforms. The first one is the installed performance of the antennas. So when you're picking out your antennas for your eVTOL platform, the vendors will provide you with a spec sheet that shows you the quote unquote free space performance of the antenna. So this is really important to keep in mind because that performance shown on the spec sheet is the performance of the antenna on some finite ground plane, or maybe it's on a cylinder of some sort, but it's a very idealized performance of the antenna. When you actually mount that antenna on your eVTOL platform, it's going to interact with that platform, and those interactions may change based upon the material properties. As Cody talked about earlier, there's a lot of CFRP. And so these interactions change the performance of the antenna. And so what it can do is it can create lobing, it can create nulls in your antenna pattern. And these are the sort of things that you need to know as you're integrating RF systems onto your platform. For example, the installed performance of an antenna, if it has a large null in a particular direction, you may not be able to close a communication link or a GPS link. You also want to know the installed performance for radar systems and other sensors like that. So again, it's really important that we understand how these antennas perform as mounted to the platform, but not only from the radiation point of view, but also thinking about the coupling between all the different antennas on the platform. I'm going to show some slides here in a moment about the RFI problem, again, radio frequency interference. The antenna to antenna coupling is very important there because we have to think about it in a wideband sense. This is not just a narrow band problem. As you'll see in this presentation, the interference can happen far out of band. And so because of that, we need to understand how the coupling performs in a wideband sense. So RFI, again, this is looking at all your transmitters and receivers on the platform and looking at ways that they can interfere with each other, both in band and out of band. The obvious problems are co-channel interference, which usually can be mitigated through frequency planning. Most of the interference problems that we run into on eVTOL platforms is due to out-of-band interference. So these are things like harmonics of the transmitter or spurious emissions of the transmitter and spurious responses of the receiver. And then there can be other kind of nasty things called intermodulation products, which are due to nonlinear devices in the RF front end of the systems. So, the question always comes up, well, can't we just go out and measure the installed antenna performance, measure the antenna to antenna coupling? We can go through test matrices where we turn on and off transmitters and receivers and look for interference. And the answer is absolutely, you can do that. It tends to be very expensive and time consuming to take that approach. Simulation offers a lot of flexibility and insight that you don't get through measurements and can generally save you a lot of money. So we're big believers in simulation, but measurements are also important. So our goal with simulation is to reduce the amount of measurements that we need to perform. Next slide. Okay, so for the antenna modeling, the first thing that you should be thinking about when you're picking out your antennas, if you want to simulate the performance, when you talk to your vendors, ask them if they have encrypted component models for the antenna. If you don't do this, what you're going to get is a spec sheet, a specification sheet for that antenna. That's going to show you the OML, usually of the radome of the antenna. You may have some general idea what the antenna is. If it's a GPS antenna, it's most likely a patch, maybe a blade antenna or some other type of antenna. But you don't have the details. You don't know the geometric details of the antenna, the material properties. Is there a matching network that's included with that antenna? So you're just not going to get that type of information on a spec sheet, and a lot of time vendors don't want to provide that information because they consider it to be their intellectual property. And so they guard it very closely, which is understandable. So a way to kind of get that information without revealing the IP of the company is something called encrypted component models. Most of the standard computational electromagnetic tools available can use these encrypted component models, and then you as the integrator, that component model has all the details exposed to you as the user. So it's kind of the best of both worlds in that situation. You get the information that you need, and the vendor has their information protected. In the absence of encrypted component models, we then have to reverse engineer the antenna. So we take that spec sheet information and our knowledge of antennas, and we start coming up with an electrically representative model for that antenna. And so this approach, it works. It generally works better for the in-band performance of the antenna because, again, if you've got a matching network or some other detail on that antenna design that you don't know about, you're probably not going to be able to capture that in your representative model. So in either approach, we have a model for the antenna's performance in free space. We compare that with the spec sheet performance, and we see good agreement. At that point, we mount that antenna onto the platform and we simulate the installed performance. Next slide, please. Okay, so the other part of the problem is this radio frequency interference or co-site interference problem. Um, on almost all of your VTOL platforms, you're going to have many transmitters and receivers and transceivers, and they operate over diverse frequency ranges. We can have really low frequency systems, maybe down at HF, and really high systems, potentially as high as like W band or Ka band. Um, and they all have to, again, coexist. If we turn on a transmitter and we lose our GPS receiver, that's not acceptable. We have to fix that problem. So what we do here at EMA is we look at both the in-band and out-of-band performance of all those transmitters and receivers. We consider nonlinear effects. So maybe I've got a low noise amplifier in the front end of a receiver. Well, those amplifiers can generate intermodulation products, which can then cause interference to the receiver. Those are not obvious interference problems when you first look at your list of transmitters and receivers, and it really depends upon the various transmitter signals that are going to be present on that nonlinear device and what types of intermodulation products they may generate. We may also have to consider things like clock signals. And so with throughout all of this, again, what we're trying to do is identify interference problems, and then we can hand those off to a test organization and say, okay, here's a list of transmit receive channel pairs that we need you to go verify whether interference exists or doesn't exist for those combinations. Next slide. Okay, so you as the system integrators, you want everything to work together. You want no interference problems, and that's one of our goals here at EMA is to get involved in these designs as early as possible and to assess the systems that are being integrated onto the platform. And this types of questions that we're trying to answer at the very highest level is, are we going to have interference problems? Second, if yes, what are the specific channel combinations? You may have a transmitter or a receiver that can support tens or hundreds of channels where you can tune the transmitter or receiver. Well, if you only have interference problems on a small subset of the possible channel combinations, the mitigation, the solution to your interference simply may be don't use that channel combination, which is sometimes quite often is the mitigation. What's the magnitude of the interference? If it's, you don't have that luxury of changing channels, how much interference are you seeing? Is it 3 dB of interference? Is it 30 dB of interference? How I approach solving those problems varies greatly depending upon the magnitude of the interference. And then ultimately, how are we going to mitigate the problem? If you're early in a design, you may have the luxury of moving antennas. That's not often the case. Usually the antennas are, their locations have been picked and they're not going to change. Again, you can try to use different channel combinations, and oftentimes that is a very cost-effective solution to interference problems. If you're not able to change the channels or change the antennas, you can try adding filters. That's not something people typically want to hear because that's extra cost and weight for your platform. And then there's a number of other additional mitigation strategies that can be deployed depending upon the specific problem that we're considering. Next slide. Okay, so I've talked about this a few times already, in-band and out-of-band performance of transmitters and receivers, and interference can be categorized in the same sort of way. We have in-band interference and out-of-band interference. And so what does that mean? So for in-band interference, if we look at this little cartoonish example for a transmitter and receiver performance here, the blue trace is the receiver wideband susceptibility. Okay, not sensitivity, but susceptibility. And so by susceptibility, what we mean is the ability for an interfering signal for an out of band interfering signal to disrupt the performance of that receiver in some way. So the red trace is the transmitter emissions. So you see the big peak at 100 megahertz. That's your fundamental signal. That's the in-band or desired transmitter signal. And then you have harmonics of that at 2, 3, and 400 megahertz. So while this is a very simple representation of how actual transmitters and receivers perform, it is illustrative of the interference problems that we see. So in this example, we have both an in-band interference problem due to the second harmonic of the transmitter that falls in the pass band of the receiver, and we have an out-of-band interference problem where the fundamental of the transmitter at 100 megahertz is falling into a spurious response of a receiver. And of course, we cook this up, right, to show these two different types. But we've seen this oftentimes in our consulting practice, where actually both types of interference are happening or occurring between a transmitter and receiver. And these are the ones that are really hard to track down because the in-band interference problem is pretty obvious. We can, okay, the second harmonic is at the same frequency as the received channel. But the out-of-band spurious response of that receiver, unless you've measured that receiver, you probably don't know that that spurious response exists. And so then one can spend a lot of time troubleshooting and trying to understand what is the source of this interference problem. Next slide. Okay, so let's take that concept from the previous slide just a step further. So what I was showing you before was just a very simple overlay of a transmitter channel and a receiver channel, and pointing out the importance of the wideband performance of both the transmitter and the receiver. But it doesn't stop there, right? Because in a true RF architecture, we have other components. We have filters, we have cables, amplifiers, multiplexers, and we have to consider the antenna to antenna coupling, something I touched upon earlier. So the good news is that for a lot of these components like filters and cables and amplifiers, vendors are becoming better about providing measured data for their components on their websites. So you can go to the vendor's website and download the S parameters for these various components and import those into your simulation tool. We use a tool called EMIT, EMIT, which is developed and maintained by ANSYS. There are other products out there, but that's one that we prefer to use. And so you could import those S parameter files into the EMIT tool. And so you can, and then for the antenna to antenna coupling, you could simulate the antenna to antenna coupling. You can use our tool, EMC Plus, and there's a bunch of other computational electromagnetic tools that you can use for that antenna to antenna coupling. But the big question is, where do you get the data for the actual the radios, the transmitters and receivers? So historically, what people have done here is they'll go to the vendor and they'll request a spec sheet, a specification sheet. And these typically provide very high level information about the transmitter and receiver. They'll contain information such as the harmonics shall be at least X dB below the fundamental signal. Maybe that's 60, 80, 90 dB below the fundamental. And similarly for the spurious emissions, there will be a threshold that spurious emissions shall not exceed a certain amplitude. That information is really pretty limited because it's giving you a worst case scenario. And if you plug that worst case scenario into your simulation tool, oftentimes what you're going to see is you predict a lot of interference problems. And then what happens is you end up going out and testing a whole bunch of interference scenarios and finding that really truly only a small subset of those cases represented true interference. And so what we do here at EMA is that we measure the transmitters and receivers with our ARMS technology. And again, ARMS stands for Automated Radio Measurement System. And so we connect directly to the RF port on the transmitter or the receiver. For a transmitter, we're measuring directly what's coming out of that RF port. And for the receiver, we're measuring the susceptibility. And I'll talk about that in a bit more detail on the next slide. But one thing I want to point out here, sorry, yeah, if you look at this plot on the left-hand side for the transmitter performance, we're showing you the parametric model based upon the information the vendor provided versus what we measured. And these harmonic amplitudes can be off by 30, 40, 50 dB. That's a big deal. That's why you get a lot of false positives in your simulation. Similarly, the parametric model has no information about the spurious emissions. Again, you may see a threshold value from the vendor, but no specific information about the frequencies at which those spurious emissions are occurring and the amplitudes of those emissions. And I don't want to dwell on this too long, but I just want to point this out. Spurious emissions generally, not always, but generally are significantly lower than the harmonic amplitudes. But we also tend to see those spurious emissions close to the fundamental frequency. This is important because you have transmitters and receivers that are in close proximity to each other on an eVTOL platform. So you don't get a lot of isolation between the two signals, between the spurious emission and the receiver. And if the transmitter and receiver are operating on similar but different frequencies, one of these low amplitude spurious emissions often is the source of interference. So yeah, don't let the low amplitude of these signals mislead you here. They are very important for the interference scenarios that we consider. And then similarly for the on the receiver side, The vendor spec sheets are often grossly inaccurate about the selectivity of the receiver, and they often provide almost no information about the out-of-band spurious responses of the receiver. So here's a good example of that. This is a GPS receiver tuned to L1, so 1.75 gigahertz, and we can see how much wider the selectivity is of the receiver versus what's stated on the spec sheet. And then there's this spurious response at 1.28 gigahertz. This is not L2. This is just a spurious response of the receiver. And if I put, negative 20 dBm or so of power into this receiver, I will start to see degradation in the carrier to noise ratio for the GPS signal. And if that power level is high enough, eventually I will lose lock on my GPS receivers. This, again, really, really important information. If you don't have this type of information, you're just operating in the dark with regards to the interference problem. Okay, next slide, please. Again, just a little more about the ARMS system. I want to point out three things here. For transmitter measurements with the ARMS, we use a custom set of filter banks, and this is important because we want to have very high dynamic range in our measurements. As I noted on the previous slide, those low amplitude spurious emissions and harmonics, they are important to characterize. And with the typical spectrum analyzer, you're going to get like maybe 80 or 90 dB of dynamic range. With our custom filter bank approach in ARMS, we're able to achieve anywhere from 130 to 150 dB of dynamic range. And so we're able to resolve those very low amplitude signals. For the receiver measurements, this is where we characterize the susceptibility of the receiver. So what we do here is we inject the intended signal into the receiver, and we establish a baseline performance metric. So that may be a certain SINAD value or carrier to noise ratio. It depends, the metric depends on the type of the radio. And then while we're injecting that intended signal, we simultaneously inject an out-of-band signal, and we sweep that out-of-band signal both in amplitude and in frequency. And so by doing so and monitoring that performance metric, when we start to see it degrade, we know that we're at that threshold where we're going from no interference to interference. And that's how we created the trace shown on the previous slide for the GPS receiver. And then finally, our measurements are automated. And so this is really powerful, especially when dealing with multi-channel transmitters and receivers. We want to minimize human interaction and the time it takes for a technician to sit there and push buttons and control the measurements. And so we can automate these measurements and save a great deal of labor hours in the process. Next slide. Okay, so value proposition. I think it's probably pretty obvious here, and this also applies to the material that Cody was showing earlier. But the earlier that you start thinking about the environments that your VTOL platform is going to operate in and the RF systems that you're going to integrate onto those platforms, the earlier that you can start to find problems or ways to optimize your design. There may be a lot of different ways to solve a problem, but what's the most cost-effective one while still providing the platform with the protection that it needs? And so that really is our value proposition here, is to help us get involved early so that we don't find these problems as some late stage test where if there is an issue, it may be one where you have to go back to several previous stages in the design process to resolve that issue. Okay, next slide. Okay, so I think I'm going to hand it back over to Nicole or Matt at this point.
Thanks, Matt. We do have some questions. Part 2325-15 says an airplane approved for IFR operations must meet the following requirements unless an applicant shows that the exposure to lightning is unlikely. Is there any guidance on showing that exposure to lightning is unlikely?
That's a really good question. And I do believe it's possible, so that if you're considering your operational environment, cities that you will be operating in. You know, there's a lightning density map that exists for the world that says, here's the occurrence of lightning in these areas. There are some spots like Florida that get struck a lot with lightning. There's other places like on the West Coast that don't have as many occurrences of lightning. And so I do believe that based on altitude, size of airplane, operational map, and then conditional operations, so that if you're performing flights or you're restricting operation, you know, so IFR, like was mentioned, there are ways to make an argument that lightning is unlikely. And so, yes, I do believe that's possible to pursue. I also believe it's possible, as I said, to pursue a reduced environment so that you can adjust the risk and amplitude of lightning to account for some of those considerations. I think it's more acceptable to the authorities to say, I'm going to protect to lightning, but here's the lightning that I think I'm going to experience. And so some level of protection, I think, is more tolerable than completely avoiding it altogether. But I do think it's possible depending on what you're willing to live with your modes of operation for the aircraft. It's a good question.
Thanks, Cody. The next question is VTOLs are generally smaller vehicles made of CFRP due to weight requirements. To provide lightning protection, some metallic parts are supposed to be included, and due to weight restrictions, it should not have a large width. This imposes some challenges on how to define the mesh cell, which captures these important features dedicated for lightning protection without violating the bundle packing factor. How to mesh the small features without violating the packing factor and generating instability.
That's a good question. So that's quite a detailed simulation question. There are ways, so relating mesh size, resolution of features, and having stable solutions to the problem. I think it's perhaps too complicated of an answer for this forum here. I'd be happy to address that one outside, but there are ways to accommodate, you know, with your particular cable types, shielding, diameters of cables, and incorporate them into the platform and get solutions that are adequate for what you're looking at. So I'm happy to answer that one off of this webinar here.
Thank you very much. Who controls the intellectual property that is created from simulation, and once created, can a model be utilized for additional use cases?
Yeah, so the way we handle it is that if CAD data is provided to EMA, simulations that are performed, that is the customer's data. They own all rights to that. EMA does not claim rights on platform results of any kind. And so that once that model has been developed, utilized for design or certification purposes, that belongs to the customer. If they want to take it in-house and run their own simulations with design changes, post-certification, that's something that's totally acceptable and a great path. At the same time, EMA can support those activities. So if you don't have the capability internally, it's something that we can support as well.
Thank you. Matt, this question is for you. It says we use radios that support many channels. Does your ARM system, well, excuse me, I'm going to have to paraphrase here a little bit. What interfaces does the ARMS system have the ability to work with? Is there saying standard bus or other interface?
Yeah. Okay. Gotcha. Yeah. So before I address that, I want to raise a point that I forgot to mention during the presentation. You know, Cody touched upon this during his part of the presentation. These VTOL platforms are going to be operating in urban environments. And for the RFI problem, this is also something to keep in mind. You're not just worried about the RF systems on your platform. So if you're going to be operating in an urban environment and there will be a lot of external RF systems, you'll also need to keep that in mind and try to incorporate that into your RF system designs. You may need to have extra filtering for out-of-band interference due to those transmitters. So I just wanted to mention that before I forgot about it. Okay, so to the question. So this may not be so applicable to this audience, but a typical bus would be like a mil standard 1553 bus, which is used with a lot of military radios, which has standard. It's a standard protocol for communicating and controlling the radio. And similarly, there are other standard buses that are used for commercial radios and sometimes non-standard. So there may be a custom interface that the vendor provides for controlling their radio. That can be really important when we're using the ARM system with those specific radios. We don't want to have to, neither you, the customer, nor we, EMA, want to sit and have to design something from scratch. And so typically what we do is we work with the vendor to get access to the software that's needed to control the radios. And most of the time that is something that is possible.
Thank you very much. That is the end of the questions that we have at the moment. If anybody else has one, please put it in the Q&A quickly. Okay, I believe that is the end of our questions.
Great. Thank you all for attending. I do want to mention that we do have a 12-hour workshop coming up that we are hosting on January 29th on HIRF and Lightning certification. So we'll dig deeper into best practices and approaches to achieve certification. Matt and I will be sending out more information on that as we follow up and provide the slides and recording. Thank you all for joining, and have a great day.
Thank you, everybody.
Thank you.